Wait. C'est comme au cinéma, like in the movies.
Yeah. Use all these equipment.
Okay, so today we are going to do the last part of chapter 4 about the garden of permutation. So I am going to introduce another definition of the Robinson-Sussnet-Knuth correspondence. We have seen 3 different definitions. Now that's the last one with the local algorithm, or sometimes it's called growth diagram, and this is mainly due to Sergei Fomin and some other paper also, a lot of paper by Van Leuven.
Is that Christian Kratenthaler?
Yes, Christian Kratenthaler in the back. So here is a local algorithm of growth diagram. So I have designed a 5x5 grid. The yellow point are point of a permutation. And in each vertex, we are going to put some Ferrer diagram. And the construction is going to be according to some local rule. Some notation. If you have a Ferrer diagram, I define the operator U index I when you add a cell in the Ferrer at row number I, if possible. If not possible, it gives you 0. And I will denote U index I of alpha equal alpha plus I when this operation is possible. Mean you add to the Ferrer diagram a new cell at the row number I. Like this one, it's possible to add a new cell or here or here. And that's the definition of Fomin algorithm local rule. So I suppose you know alpha, beta, gamma, which are Ferrer diagrams. So this is an elementary cell of the square lattice. I suppose you know alpha, beta, gamma are 3 Ferrer diagrams. And there is 4 different cases. The rule is to define delta as a function of the triple alpha, beta, gamma. So if beta is different of gamma, then delta is a union of beta and gamma. Second case, if beta equal gamma, then there is 3 subcases. So if beta equal gamma and alpha is different of beta, so this means in fact that beta is obtained from alpha by adding a cell at level I. I suppose that between alpha and beta there is just a difference of 1 cell. Beta is obtained from alpha by adding a cell at level I, alpha, beta equal gamma. Then delta is obtained from beta by adding a cell at level I plus 1. Now the second subcase, alpha equal beta equal gamma, which divide in 2 subcases. So if alpha equal beta equal gamma, if you have the grid on the square lattice, it's a point of the permutation, then delta is obtained from alpha, which is equal to beta gamma, by adding a cell at the first row. And if the cell is not a point of the permutation, then delta equal alpha equal beta equal gamma. So it seems complicated. This is local rule. In one of the elementary cells of the grid, if you know the triple alpha, beta, gamma, then you can define the new Ferrer diagram delta by this. This is called local rule or growth diagram because the diagrams are increasing when you go from alpha, beta, gamma to delta.
Sorry, I didn't understand.
Which one? This?
Yes, alpha equal to beta equal to gamma.
Alpha to beta equal gamma. And here I have a point of the permutation. In this grid,
Oh, I see.
you remember here? For example, here I have a point of the permutation. Here I don't have any point. So here we know the 3 diagrams are the same. Then I add a new cell at the first row. let's take another one. For example, if beta is the first case, beta is not equal to gamma, is different from gamma. So here, for example, they are different. Then the new cell is a union of the two. Or what else?
How do we define
Union of the Ferrer. You have.
Put the bottom left cell.
Yes, you put the two Ferrer, one Ferrer here, other Ferrer. You put the two Ferrer one over another, so that they have the same southwest corner, and you have the union of the two. Here it's different. You put them on top. The union as a subset of the square lattice. Each Ferrer is a certain subset, like the three cells. The union of the two is this plus union of this, which gives you this. Here I am in a case, see the three are the same, but I have no point of the permutation. So the new one is the same as the alpha equal beta equal gamma equal delta. Here I have alpha equal beta equal gamma equal delta, but I add a new cell because I have a point of the permutation.
And the top right corner is also.
And here, for example, yes, I have the same, but here it's not. So I am the first case on the left. This case is this one. Beta is different of gamma. No. No, here. No, they are equal, but the one is not the same.
So you add 1.
So I am adding one
In the next.
in the second row, because from this, you see, this is interesting. From this to this, I am adding a cell in the first row. So the rule is I am adding a cell from this one in the second row, I plus 1.
So you will always, your alpha and beta, that will always only differ by 1 cell.
Yes, I am going to prove this is the rule, but recursively you can prove that if you start from here with this rule applied, then the rule will be preserved in all the algorithms. So each time you will prove that from one diagram to other, else they are equal, or else you add a new cell from one diagram to the other one.
Can you go back to the rules?
So you have to prove recursively that with a certain starting initial state, I will have always this condition that if beta is equal gamma and alpha is different of beta, then one of these two Ferrer can be obtained from alpha by adding a new cell. I suppose that this is going to be true by recursion when the algorithm is going to work. Okay. So this is the initial state of the algorithm. I have a permutation, and I fill up all this vertex on the left and below with empty Ferrer diagram. And then when you have this, then you can start the algorithm. For example, you have three Ferrer, then you put a new Ferrer. So you can slowly, in a non-deterministic way, fill up the whole diagram. This is during the labeling process. This is an intermediate step. So there is a non-deterministic, because when I am here, maybe I am going to apply the rule to fill up this, or maybe this, or maybe here. But you can do in any way you do it, the result will be the same. This is another lemma. And this is the final state. When you have finished the algorithm, all the vertex of the grid are completely filled with Ferrer diagram. This is the final state. So first fact, I will not prove all this fact, but in the labeling process, the vertices of the grid with Ferrer diagram are independent of the order in which labeling is done. It's a non-deterministic algorithm. Each time you can choose, you have to choose one of these corners when this Ferrer is not yet defined, but three of the Ferrer are already defined. You choose one of these corners, and you go on until the end of everything is full. And I claim that this does not depend in which order you do the rewriting. Second fact, when you have a alpha, beta, gamma, delta, then in the grid for us, this is a cell of the grid, delta is obtained from beta by adding a cell or is equal to beta. Second fact, during the algorithm, if delta is not equal to beta, then the difference is only by one cell. And same from column, delta is obtained from gamma, maybe it's equal, or maybe you just add a new cell. So this makes sense for the rule when some diagram is obtained from the other one by adding a cell in row I, then I have the rule with I plus 1. So I can say the first case, when I write delta equal beta union gamma, in fact I can precise that maybe beta is alpha plus I, and gamma is alpha plus j. In that case, if each of these beta differ by one cell here and gamma differ by one cell with the row I and j, then the delta is a union of all this. It's adding at row I and row j. Maybe alpha equal beta, so delta equal gamma equal alpha plus a certain cell j, and maybe gamma equal alpha and delta equal beta equal alpha plus I. So you see, three subcases here. They are all different. Maybe two of them are equal, alpha equal beta, or maybe alpha equal gamma. That's the three subcases which give you this big case, beta different of gamma. Then, in the last row and last column, we get maximal chain of a Ferrer diagram. So what means maximal chain of Ferrer diagram? I am referring to the Young lattice. I am referring to poset. So let's take a few elementary facts about poset. A poset is a partially ordered set. And I have the covering relation. Covering relation means that alpha is strictly less than beta. And there is no gamma between alpha and beta. So you put an edge with an arrow from alpha going up to beta. This is a covering relation. And this covering relation, we can define the assay diagram of the poset. It's a diagram defining the poset. Here is the assay diagram of the Young lattice. So the Young lattice, what is the order relation? It's one Ferrer diagram is included as a subset of cell in the other Ferrer diagram. And this is a covering relation. Covering relation, each Ferrer is obtained to another Ferrer by adding a new cell. There is a mistake somewhere. Yes. Yes, an edge is missing. Same mistake. I forget to correct the mistake. And what means lattice? Lattice means that any two elements has a unique least upper bound. Sometimes it's called the join. And any two elements have a unique greatest lower bound. Sometimes it's called the meet. So for the Ferrer, the Young lattice, the meet is just the intersection of the two Ferrer, and the upper bound is a union of the two Ferrer. Union as a subset of cell of the square lattice. So it's obviously a lattice, the Young or Ferrer diagram according to the inclusion. And what means now a maximal chain? Maximal chain is a sequence of Ferrer, like which go increasing. And maximal means you cannot embed this chain in a more finest chain, which means that between two elements, there is nobody. So maximal chain is just a path, a sequence of edges in this assay diagram of the Young lattice. So that's what I was claiming. I was claiming in the local algorithm, the last row and last column, we get maximal chain of Ferrer diagram, like this. You see, this is at the end of the algorithm with the local rule. This is the maximal chain of Ferrer diagram, empty Ferrer, one cell, two cells, three cells, four cells, five cells. Each time, the Ferrer is obtained by the previous one by adding only one cell. And here is the maximal chain of Ferrer. So I claim at the end of the algorithm, I have this. And now I claim that this maximal chain, in fact, this is easy to show, that they encode a pair PQ of Young tableau. a Young tableau, standard Young tableau of shape lambda is the same as the maximal chain in the Young lattice going from the empty diagram till the diagram lambda. So example, this is the algorithm starting from this empty Ferrer with the yellow point are already this permutation. At the end, I have this. This is the final state. And I have the pair PQ. How is it a pair PQ of standard Young tableau of the same shape? So you see, when I have a maximal chain, yes, there is a question.
Yes. So in this picture, is it a coincidence that in all the cells where there is a dot, alpha equal to beta equal to gamma, or is it theoretical?
When there is a dot,
Then they are the same. Alpha
yes,
and beta.
they are all the same.
Is it easy to see from the algorithm, or
Needs to be proved, right?
No,
That's
it's
the only case you've given in that.
yes, but it was not written in the axiom of the algorithm, but it's a result that if you have the three things that are the same,
But the algorithm doesn't say what to do if you have a cell and they are not the same.
It is
See, but you can have an empty thing also with the three same. So it's not one versus not true.
You're asking the reverse direction.
no, look here, they are all the same.
But there's nothing.
There is nothing.
No, what if they are different and they, no, it has something else. Like,
That is
what
If they are different,
then it's
then
okay.
depending on whether the
Different,
different.
yeah.
No, if
There is no cell.
if the three are all the same, then depending if the fourth one is the same, then there is nobody. If the fourth one is not the same, then there is a point.
If they are different, then you
Eh?
can check whether there is something inside or not. You don't know.
Like you don't check, but if you were to check, you would find that there is nothing.
But so it's always true that whenever there's a dot, alpha equal to beta equal to gamma.
That's what he said.
Yes. So because it's registered the video, so we don't hear the question. So there are many questions in the room, and I continue. No, but many people are talking at the same time, and I cannot repeat all the comment and question. So this is, this can be exercised. All the idea you can get from this algorithm. So let's go back to the maximal chain. The final result. Maximal chain is encoding a standard Young tableau. Because each time you add a new cell, 1, 2, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5. So this standard Young tableau is equivalent to give a maximal chain in the Young lattice. So that was when you remember the bumping process, the first definition with the Q symbol, the symbol in blue on the top of the algorithm was we were doing really a maximal chain in the Ferrer diagram. Now the second, this also is a maximal chain. When you read from bottom to top, this is encoding 1, 1, 2, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5. So what I get here, it's just an encoding of P and Q, of two standard Young tableaux of the same shape. Now another fact, the maximal chain encode a pair of Young tables of the same shape. The process can be reversed. From the pair PQ, I can get back the permutation. If you give me just this pair here, you give me just PQ, then I can go back, I can reverse the algorithm and get the permutation. So if you know these three Ferrer, then you know this one. Exercise gives the reverse algorithm. I have to finish chapter 4 today, and I have some beautiful compliment, so I am not going to prove everything. I'm sorry, this class should be in 3 months, but I give it in 2 months. I have to go back to France to make there is a distinguished meeting from our good master who died 20 years ago, so I was one of the students, and we all the friends of Sultan Berger are going to meet in March, so I have to go back to my duty. So another fact, this bijection is the same as the Robinson-Schoenstatt correspondence. This I will prove that they are the same algorithm. So here is a full picture when you. So this was explained by me to Sergei Fomin was initiating this a long time ago when the curtain, when former Soviet Union opened, then he was able to go to Sweden and meet Aglefler. We spent 1 month together and explained me this very beautiful algorithm and all this. It's better to explain to somebody with a piece of paper. And, So this was in the 90s, 25 years ago. And, proof. I will prove the equivalence of RSK, and I will go in geometric RSK. I like shadow and light, so I will go back to this geometric RSK. So let's go back to the second definition of RSK. So this is the whole picture. When I put my shadow in black, then the red point, then the sequence of shadow in red, then the blue point, etc. So suppose I take a point, and I just consider this part of the diagram. Okay, so I have 3 black lines, 2 red lines, and 1 blue. So I associate a Ferrer diagram. Okay, when I have, at the end, you see, at the end of the, here, the pair PQ should be, there is 4 black lines, so the P symbol have 4 elements in the first row, there is 3 elements in the second row, 2 elements in the third row, the pair PQ. So I just make a partial part of this picture, and I associate this Ferrer diagram, number of elements of the number of black line, number of red line, number of blue line. So, okay, to each point of the diagram, I associate a Ferrer. Now I claim that all these Ferrer are exactly the same as the one given by Fomin local algorithm. So this is another definition, very simple. So I am going to prove that they are the same as the one obtained by local rule. So first, instead of taking the color blue, red, green, black, yellow, I put a number on the color. So the black is number 1, the red is number 2, the green is number 3. And then I claim that, suppose I have a square here, I have the diagram, the Ferrer diagram alpha, which is defined by this. And I have the Ferrer diagram beta defined by this. And then I'm crossing a line, going from alpha to beta, I am crossing a line of color I. Or conversely, if I go in horizontal edges, I am crossing a line with color number I. I claim that in both cases, the Ferrer beta is obtained from the Ferrer alpha by adding a cell in the row number I. I claim this elementary fact.
So what is alpha and beta?
Alpha and beta are two Ferrer diagram
What
defined by this. To each, for every vertex of the grid, but shifted by 1/2. I have the grid of the vertex blue, green, red, but I have the grid also of the vertex just shifted by 1/2. And to each of these vertex, I associate a Ferrer diagram. So I should see here, I have a certain, so the Ferrer now in the middle of this square. And I have an alpha, so I have a Ferrer here, which should be, there is 2 black. Here I should have a Ferrer diagram with 3 cells, 2 black and 1, so 2 in the first row and 1 in the second row. I cross this line, so I claim the new Ferrer will be adding a cell at row number 2. Here it will be invariant. Here I will add a cell at row number 1. So you can immediately, it's immediate, this lemma, that each time, horizontally or vertically, you are crossing a certain line, then in the definition of my Ferrer, which is here, I am just going from one Ferrer to another by adding a cell in the row number I if I cross the color number I. If I don't cross any color, then the Ferrer is the same. It's immediate by the definition. And so if I combine these two cases, there is 6 different cases. So this case where I am crossing, 2 lines are crossing the square, I and J, with different colors. Here only 1 line are crossing the square. Here no line at all are crossing the square. And here there is some line crossing, but I equal J. So when I equal J, the color of the line is changing inside the square by the construction, by the geometric construction. And maybe I am crossing, I have a point of the permutation, which in that case, by definition, this is the first black line with color number 1. So just from the geometry of the light and shadow, you have these 6 different cases. No color line, only one color line, horizontal or vertical, 2 color line, different or equal at point of the permutation. So the 6 different cases, you look carefully what happened between alpha, beta, gamma, delta. So in that case, by my first lemma, each time I am crossing a line with color I am adding in the new Ferrer a cell at level I plus 1. So here I have beta is equal to alpha plus, I am crossing this line color I. From here I am crossing this line color J. And here delta, I have obtained delta from alpha by crossing the 2 lines alpha and J, so I have this relation. Here I have from alpha to beta I'm not crossing any line, so I have they are equal. From this, gamma is obtained from alpha by adding a cell in level I, you see. So here I have beta equal gamma. In that case, because I am crossing from alpha, I am crossing color I and color I, so gamma is obtained from alpha by adding a cell at level I, and gamma equal beta, and delta is obtained from gamma by adding a new cell at level I plus 1. So check carefully. Here I have alpha, beta equal gamma, they are all equal, and I am adding a cell delta at the first row, same symmetric case as this, and here I have nothing, no line, no point of the permutation, they are all the same. So I have 6 different cases coming from very simple, all this come from this simple lemma that each time you cross a line, you add a cell at level I. If you don't cross the line, alpha equal beta. So there's 6 different cases. Now, I call this 1, 2, 3, 4, 5, 6. And then 1, 4, and 5 can be put in the same thing. Beta is different of gamma, and delta is a union of beta and gamma. So look carefully, 1, 4, 5, I go back. So 1, 4, and 5. In the 3 different cases, in these 3 cases, beta is different of gamma. Beta is different of gamma. Beta and gamma, you see, in these 3 cases. And you can check then delta is a union of beta and gamma. So I put these 3 cases in only one case. The other cases are exactly the same. And I get back the local algorithm of the beginning. So that's the end of the proof. That Fomin algorithm is the same as RSK.
Now it is clear by
It's not clear.
to beta equal to.
Yeah, that's all.
So all your questions now can be solved by using this correspondence. Okay, here is an example of permutation 42153. This is what you get applying local rule. Let's check now that they correspond to the light. I put the first color I equal 2, I equal 3. And now you can check that when you cross, see I'm crossing from this to this, and I'm crossing color 2, so I add a cell at level 2. From this to this, I am crossing the blue line, so I add a cell at level 3. From this to this, I am crossing a black line, I add a cell at level 1. Here, see? So you can check here. Here there is nothing, so all the 4 Ferrer are the same. So we can check that each time you cross one of these color line, you add a cell at row number I, if I is the color of the line obtained from the geometric correspondence. And then if you put the color here, color 1, color 2, color 3, you get some word. This word in letters 1, 2, 3, 4, 5, and this word in fact are coding the maximal chain. They are coding the Young tableau. You see 1 and 4, it's a word, I put the letter 1. 2, 5, I put the letter 2. 3, I put the letter 3. So this is called Yamanouchi word. It's kind of extension of the Dick word, of the left factor of Dick word. Each time you read such word, there is more 1 than 2. For every left factor of such a word, the number of occurrence of 1 is bigger or equal to the number of occurrence of 2, bigger or equal to the number of occurrence of 3. So if you have only 2 letters, then you get less factor of dict words. Again, this can be coded by Yamanouchi word or maximal chain or Q. This is a Q tableau. No, this is a P tableau. This is a Q tableau of RSK. First complement. There's another way. I think for me to obtain it in another way. By taking this algebra, now we are in the, this is an algebra defined by generator and relation, U and D. Take this as formal letters, where du commute, du the bracket, du minus ud is equal to the identity. So this is a very well-known algebra in physics. This is a Weil-Heisenberg algebra, the most simple, with one is a creation operator and the other is a deletion operator. And any words in U and D can be reordered by what is called a normal order in physics. You put all the U in on the left, all the D on the right. So there is this algebra, and it's possible to give a combinatorial representation of the algebra, a faithful representation by using combinatorial means. I am using some combinatorial operator in this algebra. And the operator U and D are going to be an operator acting on the Ferrer diagram. So you are adding a cell at any level, and D, you are deleting one of the cells at any level. So the position where you can add, it's a yellow point. In this position, you can add a new cell. And the position where you can delete a cell are all these pink corners. So what means the operator U, in fact, is acting, U is acting on the vector space generated by Ferrer diagram. U of this Ferrer is this plus this plus this. It's a formal sum of Ferrer diagram. There is 3 possible ways to add a new cell. Operator D, there is a, I put the point, the cell which have been deleted. There's only 2 possible ways to delete. I claim that this operator satisfies UD equal DU plus identity. So it's a complement. I just give you the intuitive idea why it's, I have this relation. Suppose I have this picture. I add a new cell here, and I delete this cell. I can first delete this and add after this. This will be the same result. There is a kind of commutation if I do first here and then here. Or also you can add a new cell here and then delete immediately the same cell. Or else you can delete the cell and add a new cell. So what you get is the same Ferrer. But if you do this, you will get the number of times you get this Ferrer is the number of yellow points. If you do the delete first and then the adding, the number of times you get the same Ferrer will be the number of pink points. But there is one more yellow point than pink point. So you really feel that UD equals DU plus l'identity. Identity comes from the fact that there is one more yellow than the corner of the Ferrer. Now, how to go from this to local rule is the following. I just give the rough intuitive idea. It's really complicated to formalize all this. It's in each of the square. This is the diagram obtained from the local rule with this is operator U, adding a new cell. This is operator D. In red, the edges, I'm deleting a cell. In yellow, this is the identity operator. So when you have a certain, take an elementary square, and then you are going, this explanation, the explanation of UD equal DU plus identity, which comes from the fact that there is one more yellow point, pink point. If you want to make some bijection, you have to make a precise definition. You have to pair 2 by 2, yellow point and pink point. So if you pair a yellow and a pink, if you pair them 2 by 2, but there is two different pairing. You start here, and this will be isolated, or maybe you do in the reverse. You put this isolated, and you pair a pink at level I with a yellow at level I plus 1. So pair every corner at level I with a yellow point at level I plus 1. So you pair them 2 by 2, and UD equal DU plus identity come from the fact there is one point isolated at the end which is not paired. So this pairing gives you a concrete way, give you an explanation of this relation, and this explanation, I speak very roughly, is put in each of this square. The explanation of the commutation, there is some bijection, there's some triple layer, bijection with some triple layer. The explanation is put in each square, and the propagation of the explanation of the relation of the algebra is going to give you the whole diagram. So it's difficult to formalize all this, but local rule come from the simple explanation of the commutation relation of the representation, UD equal DU plus E. This simple explanation is propagated in the whole, it's put in each of the square, it's propagated, and this explanation, you need a bijection between a pink corner is in bijection with a yellow point at the level above. So I and I plus 1. This is why there is I plus 1 in the local rule, because the pairing 2 by 2 of the yellow point and pink point. So once you have done this pairing, then you can propagate the explanation, and you get this algorithm. So this is the philosophy of what I call the cellular ansatz. This is a whole theory. This is a special case, the fundamental case, the RSK, and I give you a rendezvous to the whole theory. This is a special case in another course. I will hope to be able to do it. The relationship between, to attack all these combinatorics by using representation of some quadratic algebra, and the relationship is strongly related to orthogonal polynomial and history, all this. All fit together, you see, in a very nice setting, and I have decomposed this setting, this bijective matrix, in 4 different steps. This is the first step to this year. So now some extension of RSK with oscillating tableau. So we have seen that standard tableau is a maximal chain, Young tableau. Now I am going to walk to have a path in the Young tableau, in the Young lattice. So I can go up, adding a cell, and I can go down. You add some, add some cell, you delete, you add, you delete. So this is called oscillating tableau. It's a sequence of tableau, of standard Young tableau, such that each tableau is obtained from the former by adding a cell or deleting a cell. So it's a path in the Young lattice, in the assay diagram of the Young lattice. And I'm going to take oscillating tableau, starting from the empty tableau and finishing in the empty tableau. And there is a well-known fact in the classical literature, 20 or 30 years ago, it was Shela Sundaram gave the first bijection. So this is a sequence of oscillating tableau. You see, I start from empty set, then I add one cell, 2 cells, 3 cells, I delete 2 cells, 3 cells, 4 cells. So this sequence is oscillating and finishing in the empty set. And we are going to prove that the number of oscillating tableau is exactly the same as the number of involution with no fixed point. So pair PQ of tableau is permutation. I mean, sequence of 2n oscillating tableau is involution with no fixed point. A special case of oscillating tableau, it's the pair PQ. You always add, n times you add some cell, and at the halfway of the path, then you go down by deleting, reading the Q symbol in the reverse way. So if you always add, n times you add a new cell, n times you delete, then you have the pair PQ, which is a special case of oscillating tableau, but the general case gives you involution with no fixed point, which is an extension of RSK. So what is this picture? First, I don't start from involution no fixed point. I don't start from oscillating tableau. I start from the basis of this bijection is Rook placement. So you have a Ferrer diagram in here. Any Ferrer diagram and a Rook placement means you put at some black point, some rook, like in the chessboard, and there is at most one black point in each row and each column. So this is the Rook placement. I take a special case of rook placement. There is no empty row, no empty column. So each row and each column has one and only one black point. So this is an example. So in that case, you see, I have put this line. What is above this line is a dig pass. I have a dig pass. To be able, if I know dig pass, I will not be able to put a tower, a rook, in each row and each column. So let's take any Ferrer. Suppose you can put one black point in each row in each column, and put the light, do the analog of RSK with light and shadow, exactly the same. So what you get is this black line, red line, blue line, etc. And what is the only thing which changes, that when you look what is going outside of the Ferrer, for RSK you have a square, so you look everything which is going outside above, and everything which is going outside on the right, and you get the P and Q symbol. Now I get something more general. I get, if you look carefully what happens, so each time I have a black line, means I am adding a cell at level 1, at level 2, and each time I go vertically, then I am deleting a cell at level 2. Here I am adding a cell at level 1, adding a cell at level 2, adding a cell at level 3, delete at level 1, delete at level 3. So your sequence of edges that have some color 1, 2, 3, 4. When you have horizontal edges, you add a cell at the level which is the number of the color, and when you go down vertically, you delete a cell from the Ferrer at the level which is given by the color of the line. So to resume this, I take a row placement with this condition, no empty row, no empty column. I put the shadow process, then I look what is going outside, and I get an oscillating tableau. So I first claim that this is a bijection between rook placement with no empty row, no empty column, and second of oscillating tableau, starting at empty and finishing at empty set. I suppose that if you give me the oscillating tableau, I can reconstruct the blue point, the red point, and the black point. This I don't prove, but exercise, do it. The reverse bijection. So now where are the involution? They are coming. So now, if I look carefully at rook placement, they're in bijection with Hermite history. This is very easy to see. Because look, here I am going to put some number. Here I have put in red the number of cells in this. There is 3 cells, including the cell in the diagonal. Here there is 5 cells. Here there is 4 cells. So each time I am putting the number of cells which are between the vertical edges here of the green path and the diagonal, including the cell of the diagonal. So your first black point, there must be a black point in each row. So in each row here of this diagram, there must be a black point. So here I have 3 different choices to put a black point. And in blue, I took choice number 2. If I label the empty cell from left to right, this is first position, second position, third position. So I choose position number 2. Now for this one, I claim that the possible number of choice is 5. 5 is a number, it's not the length of all this row. Because once I have put the black point, this column is forbidden. So the number of possible positions is 1, plus 2, plus 3, plus 4, plus 5. I claim that each time you put a black point in the row, the number of possible positions for the next tower is exactly the length of this row, but you stop at the diagonal. So here I claim I have 5 possible choices for the second point, and I choose function number 3. See, so this was the first position, second position, position number 3. 3, 4, 5. So I took 3. Now here I have 4 possible choices for the third tower, and I take position number 2. So for this one, this was first position, second position. Position 3, position 4. This one, I take the second position among 3 positions. So I have I can put here, where I am, So I can put here, I cannot put here, cannot put here, cannot. So this was the second position. So etc. You see, so putting the tower in the rook placement is exactly giving a Hermite history. So there is a bijection. Hermite history, we have seen this in chapter 4b. So oscillating tableau, bijection with rook placement, and bijection with Hermite history. And now Hermite history in bijection with core diagram. So I have the proof that sequence of oscillating tableau are in bijection with involution with no fixed point. As soon as you prove that these rook placement are in bijection with oscillating tableau.
What decides the shape of the thing?
The shape?
Last
What?
time you had a square. Now it is some funny Ferrari diagram.
Yes, any Ferrer, but this is not any Ferrer because to be able to put some black point in each row and column, the Ferrer is going to be something which is which reaches the diagonal. There is the upper border of the Ferrer is going to be above this diagonal. If you fail to do this, then because each time the number of choice for the next row is the number of cell here. So if you are going the green path is going to be below the diagonal, then you are stuck. There is not enough choice to put your next tower
So that's
or
the
rook.
big part.
It's a dig path. This is a dig path. This is equivalent to say that you can fill each row by some rook, so that in each column there is only one rook.
It's also the same as the number of Young tableau with no odd columns, correct? So
Number of Young tableau is no odd column. Yes.
is there a direct projection?
No direct. Was there is with Miriam de Sainte Catherine. We have done some bijection. Yes, some bijection with some light, and we have given a long time ago in 86, I think. We have Miriam Sainte Catherine, we have given some bijection. A lecture note. It's a lecture note dedicated to combinatorics. And of course, the number of lecture notes in mathematics is 1, 2, 3, 4. 1, 2, 3, 4. It's easy to remember. This was a meeting in Montreal in 85, and there is a bijection between involution with no fixed point and Ferrari diagram with no odd column. And then there is a bijection with fan of a Burge, and then the fan of Dick path, and then we have a determinant, and then you can compute the determinant of Catalan number. There is a nice formula. So the conclusion is we have this nice using light and shadow, using the methodology of Hermite history, then we have this nice.
So
Yes?
in this description of the sequence of oscillating tableau, there you are not saying that it has to be above the diagonal.
Oscillating tableau, it's a sequence. There is no diagonal. When I take the sequence of this sequence, just put it on the line, all the green, there is no more diagonal, no more.
No.
What I claim is that the sequence, this green sequence, is going to be in bijection with a rook placement satisfying
No, so
this
if
condition.
I take the Ferrer
Yeah.
diagrams which come from a local algorithm,
Mm-hmm.
so I have Ferrer diagrams at every corner, and now I take a path which may cross the diagonal. Then that sequence you're saying is not an oscillating sequence of oscillating tableau.
Because it
Ah.
will hit zero. It will hit zero.
No, you won't hit zero.
If you look at there, you will.
You won't hit zero. If I take the
Yes.
local algorithm,
But yes, but starting, you have to start.
I start at the top there.
But what do you put here? Empty everywhere, it's a.
Yes. So the
So then,
But then already there is some problem there.
So you can take the left edge itself. It's 5.
Oh,
I can do 5 by 5.
yes, if you put empty, then any sequence of oscillating tableau is going to be above the diagonal. Yes, I think so. It's a.
So that's what I was looking at the figure.
If you take.
Oh, I see. So you cannot stay where you are. You have to add or delete.
Take a sequence of oscillating tableau. Say here it's the same. If you are, but this is not oscillating tableau because it's the same here in the local algorithm.
So you can't
So this is called so it's oscillating tableau, but sometimes you can rest. So so there is some other tableau. There is a vacillating tableau, oscillating tableau. You know, there is other kind of sequence where you can sometimes you can rest, or sometimes you can rest in odd position, or even position. No. So of course, if you can rest, then you are not, you can go below the diagonal. Okay, so now it's oscillating tableau where you can rest. So this is the answer to your question. So take any Ferrer now, not necessarily above the diagonal, and take a rook placement. So any rook placement. You don't ask to have one black point in each row, in each column. So now I have not the condition that the Ferrer is, you see this one is not above the diagonal. Oh, yes, but you can have any Ferrer. And when you look, you do again the light and shadow. And when you look what you get on the border, it's sometimes you do oscillating tableau. So you increase by one cell. Sometimes you decrease by one cell. And sometimes you rest. But there is two ways to rest. You can be on the horizontal edges or vertical edges. So I introduce this. I don't know. There is no name. This two-color pseudo. I should have another name, but it's some tableau where you can oscillate, and sometimes you can rest.
You're going to get two-color masking path?
Yes, there is two color. Yes, there is two kind of resting. You can rest in blue or rest in red. So you have two different ways to rest. You stop. So the tableau is going to be the same in two different ways. But sometimes you increase by one cell, sometimes you decrease by one cell, and sometimes you rest. So I claim extension. So maybe this answer to your question. Extension of the previous bijection. Now this sequence of oscillating tableau where you can rest in two different ways are in bijection with involution. Now there is fixed point. Resting is correspond to fixed point, and there is two colors on the fixed point. So this is in bijection. The bijection is the following. So do exactly the extension of Hermite history. So say if I follow my path, if I was trying to do a rook placement with one rook in each row, then I would get this. This is the first step of Hermite history. So each time you have an horizontal step, you put a chord like this, the beginning of a chord, or each time you go down, you put the end of a chord. So you have a certain word. In this means horizontal step, vertical step, horizontal step, vertical step. This is exactly what we have done for Hermite history. Let's go back to the Hermite history. You say I have three horizontal steps. So I have three starting of loops. If you remember the bijection, now I have one going down. So I have to close it. So I have the end of a chord here, and I take choice number 2, which means first, second, 2, so it's choice number 2. Then 1, 2, 3, I have three. No, I have three horizontal steps, which means I have three open chords, the beginning of a chord. So I open three new positions for the next closing of chord, and then I go down, see, and then I take position number 3, number 2, number 2. So the first step of the bijection is just, before putting the chord in 2 by 2, is just reading the Dicke path by, this is the letter X, or going up, and this is the letter X bar going down. So you have a word here. If you cut the chord, you have a Dicke path, a Dicke word, and then linking all the chords together, this is done by the choice position. So I can do exactly the same for my partial Hermite history. So just follow the path, and you get this word. It's a word in horizontal vertical step. Now it's no more a Dicke word. Maybe it can be any word. And then you are going to try to close the same way as for Hermite history. So I have a rook. Here I have nobody. I have no rook. So I don't do this one. I don't do anything. This one I don't do anything. Now I have at the third row. I have to put a rook. I have three possibilities. So here I have three possibilities. I take the first one. When I take now this one I don't close anybody. I take this one here. It's this this second part of the chord. So I take this one, and I have to put a rook. I have 1, 2, 3, 4, 5 possibilities to put a rook on this row, and this corresponds to 5 possibilities to join this chord with one. So there is 1, 2, 3, 4, 5, and I take choice number 1. So each time you put a rook, you are going to close to join the end of the chord with the beginning of another chord, according to these blue numbers. But at the end, what remains is some chords are not. There is a beginning of a chord which nobody has closed, and there is the end of a chord that nobody has closed. So this beginning and end correspond to the empty row and empty column, and this corresponds to the fixed point of the involution. But there is 2 colors for the fixed point. It can be like this or like this. Beginning of a chord, which is not closed. The possible end of a chord, which corresponds to empty row and empty column. So this is what I claim, that this kind of oscillating tableau with possible rest in 2 different colors are in bijection with involution with some fixed point and 2 colors of the fixed point. Now, in special case, where the Ferrer diagram is in fact a staircase. So now you know you don't have to put colors. According to if the letter is odd, the index is odd or even, you know if you are in horizontal step or vertical step. So you don't need to put color in your fixed point. Now there is the fact that it's very well known that the rook placement in a Ferrer diagram, which is a staircase, with maybe some row and a column that are empty, any rook placement are in bijection with a partition. Find the bijection between the rook placement in the staircase shape and partition of set. There is a bijection between partition and rook placement. And in fact, the bijection is such that if you have n row in column and k rooks, then the partition is on n+1 element and have n+1 minus k blocks. There is a shift by 1 in the size, and the number of blocks is going to be the number of empty column, which is the same as number of empty row. So rook placement on the staircase shape is the same as set partition. You see there is 5 rooks, and 1, 2, 3. There is 3 empty columns, and there is 3 empty rows. 3 empty columns, 3 empty rows. So there will be 4 blocks, and on the size will be n+1. If you have only one cell, there is 2 possibilities: empty cell or put a point, and there is 2 partitions with 2 elements. One have 1 block, the other have 2 blocks. So put some light in your rook placement. It's an obsession of light, but it's enlightened the solution of many problems. So you get a kind of you see, if you read the border of you get oscillating tableau with some you can rest, but now according to the position of the rest, which is odd or even, you know if you rest on the vertical edges or horizontal edges. So you don't need to put colors. And you see this is the oscillating tableau with rest. So this is a sequence of oscillating tableau with rest, and here I have put each time I increase by 1 row, I put a vertical black line or horizontal black line, and there is some rest. You see in green, I rest. So I propose you the following exercise. First, read this paper. Read only what you need. Well, it's a good exercise for if you want to do research. It's instead of reading the whole thing, extract the information you need, because they prove in this paper that rook placement are in bijection with sequence of vacillating tableau. So vacillating tableau is this kind of tableau where you can oscillate and you can rest. But you can add a cell or delete cell or rest only on certain position. If you are on an odd or even position, you have a constraint. There is a different rule which is going to give you hesitating tableau. The rule is different, but the 2 seconds are in bijection. So first, read the definition of vacillating and hesitating tableau and prove the theorem by using, because they prove the theorem by using local rule. I forget to say that all this lighting is equivalent to local rule, because each time you can put Ferré diagram everywhere. Each time you cross a line of certain color, you can put. So I forget to say that local rule on every of this diagram, the beginning, local rule here, giving the oscillating tableau, is the same, exactly the same as putting the light. So if you prefer, some people prefer local rule, or some people prefer the light, so you can choose which one you prefer. And in this paper with Stanley and co-author, in fact, they prove everything by local rule, extending the local rule for the permutation for a grid in any. But prove this, prove this by light and shadow. So read the part of the paper you need, and reprove it by using the light and shadow. And now even there is a new paper by Joshua Vergès, stammering tableau. So c'est tableau in French, tableau vacillant, tableau hésitant, et tableau bégayant. So all the tableau, you see there is a. And in fact, what he's taking is instead of a staircase, he's take a double staircase, meaning you put two orthogonal edges, one vertical, two horizontal, one vertical, two horizontal, one vertical. So there is twice more columns than row, and also he has some nice things related to the PASEP. The PASEP is behind all this. So maybe if you have courageous to read this, but in this paper he put at the same time the local rule and the light also. Well, he's French, he was very influenced by the Bordeaux school, and he liked also light and shadow algorithm. So all we have done since the first lecture on the RSK is in fact RS, Robinson-Schoenstatt. Now I am going to do RSK, or maybe just a hint of how to do RSK. So I see Donald Knuth, he has an organ in his house, and so this was due to Donald Knuth, so this is what RSK. So it's an extension of RS, permutation, to matrices. So take a matrix, this means 0, there is a point is 0, with some entries, 1, 2, 3, 4. So what the idea I'm going to show is that in fact, this RSK is a special case of RS. The extension of RSK, and go back to RSK. So to go back to RSK, what I do is I put each one, I put 1 point. When there is a 2, I put 2 points. But I need to have a permutation. So what I do is just when you have 3 points like this, you shift a little. By epsilon this one, you lift up epsilon, 2 epsilon, 3 epsilon. You just move a little the point like this. Vertically, move a little the point like this. When you have several points in the same box, you move them like this. In fact, there is 4 different ways to move the point so that there is only 1 point, at most 1 point in each row and column. So you move a little the point. So this gives you this, from this matrix, I get this, and then I apply RSK. With my favorite RSK, you will understand. And you see all this, the 1, 1, 1, they're on the same row. Here I have 1 point, here 2 points, so this there was 3 points here, so they were on the same row. So this is 1, 1, 1. And here this is 2, 2, see this is the 3, 3, 3, they were on the same row, this is 4, 4, see, 6, 6, so I put this was the previous value of these points, but now they are increasing, and in purple, all these 5 points were on the same column. Now they become 1, 2, 3, 4, 5, the altitude of the. So you see, this was the first row of the matrix, second row, third row. So I have many points of the same value, 4, 5, 6. This was all the point. This was the first column, second column, third column. And then you apply, you put RSK by putting, for example, I'm going to put 1, 1, 1, all this 1, 1, 2, 4 is going to be the first row of the P symbol. Like this, 1, 1, 1, 2, 4, 7. Or here, the black line, 1, 2, 2, 3, 3, 6 will be the first row. Second row, etc. So you apply RSK for permutation, and then you identify, instead of RSK permutation, this was 1, 2, 3, 4, 5, 6, 7, 8. Now I have 1, 1, 1, 2, 2, 3, 3, 3, 4, 4, 5, 6, 6, 6, 6, 7. Here I have 1, 2, 2, 3, 3, 3, 3, 3. So you have a repetition of letters. And in fact, you have a B word like this, UV, which sometimes it's called, how it's called this? It's a two-line array or generalized permutation. For a matrix, you can go to this. So the definition, you see, it's here you put in increasing order all this number 1, 2, 2, 3, 3, 3, which are exactly the number of, this is the number of value in the first row. It's first column, second column, 2, 2. In the column number 3, there is 5 point. In this column, there is 2, 4, 4, and then in this column, 5, 5, 5, 6, 6. So this is the index of the column, repeated a number of times the sum of the value in each column. And inside each block, like this, then this number goes increasing. So this is a bijection from this to this to this. This is called two-line array, and you apply RSK on this. But this is a standard RSK for permutation. But you have to prove that now you have a semi-standard Young tableau. What do you have? You have a bijection between matrices with positive entry or 0, and a pair of P and Q tableaux, which are called semi-standard Young tableau. They are weakly increasing in row and strictly increasing in column. So you have to prove that in this process, I have strictly increasing in column. So this is a certain property because of the fact how I move my point. So in fact, RSK, extension of RSK, becomes a special case of permutation where you have something to prove on the way you put the point on the green line and purple line. So I don't go the whole proof, but then using, this is intuitive idea maybe, which these people have done, Fulton and Amri, Prasad in his book, each have written a book, and there is a way which is well known, the matrix ball construction. So I think that you can, from this intuitive idea, you can get the algorithm of Fulton, or maybe from this intuitive idea, get the algorithm of Amri. So I will ask Amri, how did you get this algorithm? Did you go through this, or did you get?
Oh, I tried to make this easier to understand.
This picture, yes. So if you try to easier understand this, then you get this algorithm. So maybe this is better. I think this is better algorithm than the. So I prefer this algorithm to.
Me too.
Not because it's a V in the front. I don't know where he finds the V, but because I prefer because this algorithm comes directly, I think, from this intuitive idea. You move the point and then apply RSK standard and then move back the point to get the notification of all the one. And so read the book of Amri Prasad in Cambridge Unity Press and exercise. Try to get the same algorithm by starting from this picture. And then even if you have an iPad, go to the Apple Store, it's free. There is an application by, so it's not Lorraine Williams is famous in the PASEP in medicine. It's not the same Lorraine Williams. This is a man. I think he was student when he gave PhD student when he gave this. I think he's don't remember university, but Lorraine Kelly Williams. There is a nice application. So you can have there is not the Amri algorithm, but there is a Fulton algorithm, and there is a shadow, and so you can play with the shadow. There is a shadow in light algorithm. There is a jeu de taquin. All this, everything about RSK, you can is available on Apple Store, You can see the shadow, you can make big permutation, and immediately you get the different shadow, black, red, blue, etc. So there is some... I will, when I will go back to France, I will put the whole references for the whole classes, but I have started for the RSK. I will do, so this is classical papers, the jeu de taquin, local rule and growth diagram. Sorry if I am missing some people and some books. Sagan, Fulton, Fomin. Fomin is an appendix to the book of Stanley, where you can really get the proof of the jeu de taquin, the dual tableau, everything. And here is the book of Amri in 2015. There is some software, and this applet in the Apple Store.
It's also implemented in Sage.
Yes.
RS.
RS. So it's become very classical. All the kids can play now. Instead of playing with video games, they can play with RS. So some complement. I cannot escape from the n factorial garden. There is some other tableau counted by n factorial, which are deeply related to physics. So remember the PASEP, we have done this in chapter 2D, the TASEP for Q equals 0. Now do the same with 2 parameters. The general model has 4 parameters, but 2 parameters, and the Q. So when Q equals 0, the interpretation of the stationary probability was with Catalan numbers. Now for any Q, it's going to be n factorial. So in this section, I have just remind you what is the Markov chain, what is the stationary probability. I will not repeat this, but the corollary of things coming before, which it's not in this class. It's a stationary probability for associated to a certain state. A state is just a sequence of cells which are empty or full. There is at most one ball in each cell. Then this probability can be expressed as the sum of the weight of some combinatorial objects which are enumerated by permutation, by n factorial. So I am going to define this alternating tableau. So the definition, I take a Ferrer diagram, but with possibly empty rows and empty columns. The total length of this path is n. N is the total number of columns plus a number of rows, possibly empty. And then alternative tableau is the definition. I put some point in the Ferrer, which maybe are blue or maybe red, or maybe nothing. Maybe you don't color any cell, you color 1, 2, 3, 4, etc. So some cells are colored blue and red with, of course, some condition. The condition is that at the blue cell, there is nothing color on the left. And for a red cell, there is nothing below. That's the condition. And I call this alternative tableau. And I claim that the number of alternating tableau of size n is factorial n plus 1. And this is not obvious from the tableau. There is different bijection. I'm not going to give them, no time, but this will be in another class related to the cellular ansatz. Example, for n equal 2, you can check there is 6 alternative tableau, which is factorial 3. So it's not obvious. Take n equals 3, you will find 24 alternative tableaux. Now to express what the physicist wants, the stationary probability, you have to define 3 parameters on such tableau. The parameter k of t is the number of cells which are yellow. A cell is yellow if and only if it's not a blue cell, it's not a red cell, it's not at the left of a blue cell, and it's not below a red cell. So you take all the color cells, erase all the cells on the left, erase all the cells below a red. What remains is a cell which are weighted. So this is going to be the Q analog. The parameter Q will be the number, Q power, number of yellow cells. So Q equals 0, no yellow cell. Such tableau will be enumerated by Catalan number. This will be another interpretation of Catalan number. It's alternative tableau having no yellow cell. Now we have two other index, I of t and j of t. The number of row without a blue cell. So I of t, see, is this, this, and this. 1, 2, 3, 4, 5. So it's 5 rows without a blue cell. And j of t, number of columns without a red cell. So there is 1, 2, 3. And then I claim, before claiming, I define the profile of an alternative tableau. So if you have a certain state in the PASEP, empty, full, empty, full, empty, full, empty, then I associate a path. Empty, full, empty, full, full, empty, empty. So I associate a Ferrer diagram. For a given state, I have a Ferrer diagram. Forget the E and D, this comes from the PASEP algebra. This comes from another thing. But for any state, giving the sequence of particles, I associate a Ferrer diagram, which I call the profile of the state of the word W. Then I can state my theorem, the stationary probability associated to a given state, which is a word in empty and full cell, is exactly the sum over all alternative tableau of Q power the number of yellow cell, alpha minus the inverse of alpha I of t, inverse of beta j of t. So this is a nice interpretation in terms of alternative tableau. And if you remember what I have said, the TASEP in the chapter 2, there was an interpretation with binary tree where alpha and beta, the inverse of alpha and beta, was the length of the left branch, the length of the right branch. And there is if I have an alternative tableau with no yellow cell, then there is a bijection with binary tree such that these two parameters become the left branch and right branch of the binary tree. This is complement to Catalan and n factorial. And of course, I have to divide by the sum of the partition function is the sum of all the weight of all the tableau to get a probability. So that the sum of all these probabilities is going to be 1. So this is a nice interpretation in terms of tableau. In fact, at the beginning, it was done by Cortel and Lorraine Williams, not the same Lorraine Williams as the application in the Apple Store. In the different papers, they give this in terms of permutation tableau. So this is another tableau. Permutation tableau, you are filling, again, a Ferrer diagram, but now there is only one color of point, the black color, and with these two conditions. So in each column there is at least one. One black. The 1 means black point, and the 0 empty point means 0. So in each column there is at least one black point, and this pattern is forbidden. That means that if you have an empty cell, and there is a black point on the left, then there is no black point below the empty cell. So they are not consecutive cells. It can be, they are not necessarily consecutive, these 3 cells. So this pattern is forbidden, and there's at least one in each column. And then they gave an interpretation in terms of this tableau. But the morality is that this is not symmetric in row and column. Alternative tableaux are symmetric in row and column, then mathematicians love aesthetic, and when something is symmetric, because the PASEP is symmetric in left and right. Particle can move in the other side. You replace alpha by beta, q by q, 1 over q. There's a symmetry in the PASEP, which is not reflected in the symmetry in row and column of the permutation tableau. Exercise, give a bijection between permutation tableau of size n plus 1 and alternative tableau of size n. So there is one more sheet by 1 and give a bijection. And this bijection, via this bijection, transport the 3 parameters for alternative tableau, put them on the permutation tableau. In fact, for the connoisseur, permutation tableau, if you delete this first condition, so it's more general than factorial. This was introduced by Postnikov, and he shows that such tableau with only the second condition are in bijection with permutation with 2 color on the fixed point. So again, we are close to something we have seen before, and it shows that it's in all permutation tableaus is related to the positivity of the Grassmannian, the Schubert cell, all this algebraic geometry, the deep algebraic geometry is related to this tableau without the first condition. And he gave a bijection between this tableau and permutation with the 2 color on the fixed point. But if you put this condition, then there is it's exactly permutation. And then there is other tableau, tree-like tableau, staircase tableau. There is 4 different tableaux, all in bijection, which are enumerated by permutation and which give also interpretation for the stationary probability. So there is a whole combinatorics behind this. And I tell you this story because it's related now to the Q-Laguerre polynomial. So in chapter 4b, we have seen Q-Laguerre polynomial. First, number 1, this was the Q-Laguerre history, the choice function. So you remember the Q-Laguerre history when I have my permutation in bijection with the Laguerre history, and I put Q power 4. It was Q power, the sum of all possible choice in all the history. So this was what I call the Q-analog of Laguerre history. So it's very natural to put Q power I each time you are choosing choice number I. And then the beautiful fact is that the distribution of this parameter Q among Q-Laguerre history is the same as the distribution of the parameter Q among alternative tableaux. So the Q
You have alpha beta, no alpha.
is more complicated. But if I just take the Q coming from the Laguerre history is the same as the Q coming from the number of yellow cells in the alternative tableau, which is the Q which is related to the PASEP. And the corollary, the partition function corresponds to the sum of all the weight, and it corresponds to the moment. We have seen what is the moment of an orthogonal polynomial. So if I put alpha equal beta equal 1, then the moments of the Q-Laguerre, first kind, are exactly the partition function. So this moment, you remember, it was complicated. It was given by these people. They were working for the PASEP, with this BK lambda K. But if you put alpha beta, then it's more complicated. It's more or less the left to right minimum element, right to left, but it's a little more complicated. So this will give you a Q-Laguerre with alpha and beta with 2 parameters. So this is why I want to show you, because the Q-Laguerre, which is maybe difficult, the moments are difficult, then it's really related to this alternative tableau in PASEP. Okay, we have seen Q-Laguerre 2. If you multiply by Q power the number of choice, then you get n factorial. So this is not at all the Q you need for the physics. So again, this alternative tableau, there is a bijection with permutation, which came from the same spirit as we have done. But we have not done, but we have shown that a representation of this algebra leads to the local rule of Fomin. I have not shown at all, but I give you just a rough idea about the propagation of the explanation of this from a representation by some operator acting on the Ferré diagram. And this physics is related to this algebra, and there is again a representation by operator, which are really related to Laguerre history. There is 4 different ways to add a new point in a binary tree. You open a new cell at the left, open a new cell at the right, no open cell, or close everything. There is 4 possible, and this gives you a rotation with this. And then this rotation gives you the bijection. So there is same philosophy, you see, and there is other example. So all this is, I put them in the same roof, which I call cellular on that. It's a long story, and this goes much beyond this first class of combinatorics. So I will finish. I have 5 minutes, if you allow me, because this is a complement for the chapter 2 and chapter 3 for both Catalan and factorial garden. So we have seen lattice, assay diagram. We have seen the Young lattice, the poset, and an example is the Boolean lattice. So when you have a certain subset of a set, you can encode this by a word in 0 and 1. A is included in B, means a subset is this, and the poset is this. The order relation for the Boolean lattice Once you encode a subset by a word in 0 and 1, it's just you change some 0 into some 1, and you are increasing in the Boolean poset. So we have seen in chapter 1 and chapter 2, there was some permutation, increasing binary tree, canopy, up-down sequence. So this is a permutation, up-down sequence, the related binary tree, the canopy of the binary tree, and there was an exercise to show that this is the same. Now there is an order relation on permutation, which is called the weak-Bruyère order. So this is the assay diagram of the weak-Bruyère order. So there is two weak-Bruyère orders, the right and the left. So the right means you exchange two consecutive values. Or the left, which you exchange two values which are consecutive. For example, so this diagram is for the left weak-Bruyère order. For example, here, this is below this one, you are exchanging 1 and 2.
If you invert the...
Yes, it's the same because it just takes the inverse permutation. You exchange, took the indices or the value is taking the inverse permutation. So here I'm working with the inverse permutation. So here I exchange 2 and 1. They are not consecutive in the word, but they are consecutive value. So this gives you this assay diagram. So this gives you an order on the permutation. And there is three structures. So counted, this Boolean lattice, its word in 0 and 1, they are counted by 2 power n, or n minus 1. Here it's trees, Catalan. This is trees, and this is permutation. So I have a certain order on permutation, which is a weak Bruyère order. I have some order here, which is a Boolean lattice inclusion. I have again an order on trees. I want to finish this chapter 1, 2, 3, 4 with the Tamari order. It's a very beautiful order. So the Tamari lattice, this is the Tamari flower. So Tamari is this. Take a binary tree, take two vertices S and T in this position with some subtree A, B, C, and exchange to do this. This is called a rotation in the binary tree. You see this blue, red becomes this. ST become ST. It's like associativity. Take the product A by B multiplied by C is the same as A multiplied by product BC. It reminds you associativity, reminds you parenthesis. Yes, there is some comment. So this is called the rotation. And this is called the right. So I am going to do always rotation in one side from this to this. This will give you an order relation. And proposition, this order relation, give you a lattice for the binary tree, which is called the Tamari lattice. So here is an assay diagram for the 14 binary tree. This is the minimum element, the biggest, and this is assay diagram of the Tamari lattice. By doing always rotation in the same way. So this is Tamari, and it introduces, not in terms of trees, but in terms of parenthesis system, in 51 in French, monoïde préordonné et chaîne de Markov. He was a German during the war with the Nazi, and he escaped from Germany, and he changed his name to Tamari. Now we know increasing binary tree. When you project an increasing binary tree, you get a permutation. So I claim that if you get two trees which are increasing, one is less than the other one in the Tamari order, if you take permutation related to these two trees by the increasing binary tree, then the two permutation will be also increasing in the weak Bruyère order. So there is a compatibility between the order of trees and the order of permutation when you go from increasing binary tree permutation with underlying binary tree. And now if I take a canopy of a binary tree, then again, there is a compatibility. If I increase in the Tamari lattice, the corresponding canopy will also increase. Maybe they will be the same. One tree will be smaller than another one, the canopy will be the same. But if you go up in the Tamari lattice, then you go up. There is a compatibility. So there is a compatibility at the tree level. So there is a very beautiful embedding of the three lattices embedded in each one in another. So this is some paper, Loder Onko, Björner and Wax. So Tamari-Lattice exercise in terms of dig path means you have edges going down, find a primitive dig word, and you just exchange. So when you do in terms of dig words, the Tamari-Lattice, you increase the dig path. So Tamari-Lattice is in dig path. For the order of a dig path is below another one, it's an extension of the Tamari-Lattice. But the converse is not true. This is the Tamari-Lattice in terms of dig path, and this is a dig lattice. There is more relation in red in the dig lattice than in the Tamari-Lattice. And you have seen in this chapter 2 triangulation, these are counted by binary tree. So what is the Tamari-Lattice in terms of such triangulation? It's take a diagonal in a triangulation and just make a flip. And this also is well known to be equivalent to the rotation in binary tree. So exercise proves that doing this is equivalent to do this. And then I will finish with the geometry, realization of the associahedron. Here is a 14 triangulation, the 14 binary tree, with the edges are the rotation in the binary tree. And is it possible to realize the cell structure of the associahedron? Associahedron is this kind of thing, as a convex polytope. So people have looked a lot. Here is a 14 binary tree. In each vertex, there is a binary tree. Is it possible to realize this as a convex polytope? And yes, Jean-Louis Laudet has given a very beautiful proposition. Here is a certain, the 14 binary tree triangulation. And take a binary tree. You put the vertices in blue in order. First, second. In blue is the symmetric or in order of the binary tree. For each vertex, you put 2 red numbers. For example, this one you put 4 and 3. 4 because there is 4 external edges at the left, and 3 because there is 3 external edges at the right. So for each vertex, you put these 2 numbers. You have 2, 1 because 2 on the left, 1 here. Now take the product of this red number. 4 by 3 equals 12. This is vertex number 4. So you have the blue number, vertex in order, the red number, product of all these red numbers. Now take all these points in the space of dimension 6 and take the convex hull of this point, and you get the Tamari, you get the realization of the associahedron. It's very beautiful. You get this. You get the 14 binary tree, or the Catalan binary tree, with some edges. The convex hull of all these points give you exactly the rotation of the binary tree, or give you the associahedron. Here you take all these points in a space of dimension 6.
So each tree you have one such.
Each tree you have a point. Take the convex hull of all these points, and you get a convex polyhedron, which is exactly what we are looking, the associahedron embedded in the. In fact, exercise shows that the sum of this number is 21, is nn plus 1 over 2. So in fact, they are in an hyperplane. So Euler would be happy to apply his formula for number of vertex minus edges plus number of faces equal 2 for this one, where each of the vertex is one of the triangulation of Euler. And I finish with geometric. So there is a permutohedron. You can do the same for permutation, going to embed the lattice of permutation for the weak order into a permutohedron. Do the same, the hypercube. So you have an embedding of all these geometry. Hypercube is I call this the binohedron. This is the word of computer scientists with 0 and 1. And also the compatibility of the geometry. I will finish with this. That this is a hypercube. You cut with the knife some of the corner and you get the associahedron. You cut again some corner and you get the permutohedron. So there's a compatibility in the geometry of these 3 structures. There is compatibility in the combinatorial order. And also there is some algebra with dimension, some Hopf algebra, which are also compatible with quotient, ratio, etc. Thank you for your patience, and we finished chapter 4.